Good. How are you, Anthony?
Still tired, but still good.
Good, good. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
Tired.
Tired? I know. Yeah, me too. I feel like we're all tired. Okay. All right. So first thing, so I did manage to grade your midterm twos. I know I said probably by Thursday, but it turns out I had some time over the weekend, so I did spend some time grading it. And I just finished up this afternoon. So average on this midterm, you guys did better on this midterm than the first one. It's not going to show up properly on Canvas because if you notice, I swapped your midterm scores. So if you recall from our syllabus, between your two midterms, whichever midterm you score higher in, I count that as a higher percentage of your grade. There's no elegant way to do that in Canvas, and so the only way I can think to do it is just that your midterm one counts for 30% of your grade, and midterm two counts for 20%. So if you scored better on midterm two, I kind of swap that into your midterm one score, and then your whichever one is your lower one is in midterm two. So the average, I think, if you look at it on Canvas, is not going to be proper because it's going to be the average of everyone's low score, which I guess might be interesting for another perspective. But for this particular exam, I computed it manually, average about 36 and a half out of 50. Okay. Okay. So I did do the swapping manually, and so I definitely would double check. So I kind of just double checked myself just to make sure I entered everything correctly. But I don't have your midterm ones anymore. I did write them all down before I did the swap, but just double check the scores on Canva just to make sure I swapped it correctly. And if I make a mistake, just like okay. But I did bring the exams today, so you can pick it up. And if you're not here today, I know probably from last week, a lot of you were expecting it to be on Thursday. I'll bring the exams on Thursday as well for you to pick up. Okay. And of course, they'll be in my office as well. So if you can't stop by this week, you can also always stop by my office next week. Okay. Okay, and then I think this is also a good time to remind everyone that of the other grading policies that I have for the class. So I like to have my class average for 308 to be around kind of like a C plus range. So like kind of around 77%, 78. And so what I do at the end of the semester, once all the grades are in, so that includes the midterms, the finals, all your homeworks. If the class average is below that about 77% threshold, then I'll add points to everyone's grade until we reach that average. Okay. And so if the semester were to end today, I think this would equate to be about maybe 2 or 3 points extra to everyone's grade before I compute the letters. That's not to say that it's going to be 2 to 3 points in the end. Generally for this class, people tend to do well on the final. People tend to do better on the second midterm, just like I promised as well. So it may not end up being much at the end, but that is something I apply before I put the letter grades in. Okay. Yeah.
And just that's you're adding the same amount of points to every single person.
Exactly. Exactly. Yeah. So it's just, I'm just basically forcing the average up to 77%, and then everyone gets an equal benefit. Yeah. So that way the distribution kind of stays the same in terms of how the grades are distributed. Just the mean just moves up. Yeah. Okay, so I have the midterms today. So again, just double check your scores, just because I had to do the swap manually because there's no elegant way to do it on Canvas. Just make sure that your scores are still correct. Okay. And there's actually quite a few of you who haven't picked up your midterm one, and so if you did want to pick it up, I still have those in my office as well for you to look at. Okay. All right, and so with that, let's just kind of quickly overview what we're going to do today. So today we're going to first thing we're going to do is we're going to finish up our lecture notes on confidence intervals. We don't have too much left to do. We just basically just have one more example with that. And then we'll move on to our last big topic, I would say, which is hypothesis testing. Okay. There is one small topic after this, which is just scatter plots and regression lines, but that's a pretty short lecture. And so I think we're on track so that by next Thursday, we should be able to dedicate all of next Thursday just for final review. Okay. And also, so I haven't had a chance yet, just because I've been just trying to grade all the midterms for all my classes. But I do want to put out a study guide for the final exam before the end of this week for sure. Hopefully before Thursday, just so that you can start to get a head start on studying for the final exam. Okay. So remember, the final exam, it is going to be cumulative in the fact that there will be stuff from midterm 1, midterm 2 that's going to be on the final, but it's not going to be absolutely everything from the class. And so I am going to cut quite a few topics. So I think I gave you guys a tentative last time. So what I'm thinking right now is first order ODEs, Laplace transforms, Fourier transforms, and then just all the probability and stat stuff. So that's maybe about like 2/3 of the class that you're going to be responsible for studying. Okay. So don't study stuff that's not going to be on the final. All that stuff is still important to know, but I know you guys have a lot of finals and final projects, and so I don't want to tell you to study something and not have it be on the final exam. Okay. All right. Any questions I can answer about just the midterm or the final or just anything before we get started for today? Okay. All right. So let's go ahead and get started. Okay. So last time we were here, we were talking about confidence intervals. So let's go ahead and resume with that. Okay. All right. So just as a quick refresher, confidence intervals are basically our way. It's kind of a more formal way to express the uncertainty in a known or an unknown quantity. Okay. All right, and so remember the whole theme of this whole unit on probability statistics, that when you observe things in the real world and you know outside of the realm of theoretical math, there's always going to be some factors that we just can't account for. And we call that uncertainty. Okay. So whenever you measure something, whenever you are observing something, there's always going to be some variance in terms of what you measure, even in something as given as like a physical law, right? So I think for your homework assignment, I'm having you guys measure gravity just by dropping an object from your desk. You're going to see that you're not going to get 9.8. I would be astounded if you got 9.8 exactly, just based on how the test is set up. Okay. So confidence intervals, this is kind of our first way to kind of express, what this uncertainty is. Okay. And so there's kind of two aspects of this. And so on the one hand, there is our level of confidence. Okay. And so usually we give that the symbol gamma. Okay. So our level of confidence kind of tells us, how certain we are that in our observations. Okay. Okay. That's to say, a higher level of confidence means that, if you were to take another observation or if you were to take another measurement, your confidence tells you the probability that your measurement is going to lie within your confidence interval. Okay. Okay. So your confidence doesn't necessarily have to do with your measurements themselves. That kind of gets expressed in the interval itself. But your confidence is just, if you were to take another measurement, you have a 95% probability or 99% probability or 99.9% probability that your next observed value will be within that range. Okay. Okay. And then the second aspect that kind of has to do with this is the interval itself. Okay. So I think one thing I didn't explicitly kind of mention last time is that we are making several assumptions with this interval, right? So the way that we express our interval is kind of we take our mean value and then we add the same number. We add the number and then we subtract the same number. So we assume kind of an even distribution around our mean. Okay. And so for instance, if our mean value is X bar, right? More specifically, this is our sample mean, right? So remember, the difference between a sample mean and the true mean. So the sample mean is just whatever we observe. So we just add all the values from our observation, we divide by the number of observations. Okay. Our confidence interval is we say that our sample mean is going to be between X bar plus K and X bar minus K. Okay. Or this value of K here, we define this as our interval. Okay. So that's basically how much spread that we're going to expect to see, or how big our interval is. And this K, so there's going to be several ways for us to compute K, but based on last week's lecture, where let's say we know the variance beforehand. Okay. Okay. So our sigma squared is our variance. So let's say if we know that beforehand. So if you remember from last week, the example that we did was we looked at the uncertainty of just a very simple measurement, right? So we took just a ruler measurement of an object. And so in that case, since the only uncertainty is just whatever the uncertainty of the precision of the ruler, we can say that we know the variance before. Okay. So in those situations, our K is equal to C times sigma divided by square root of n. Okay. For sigma here, this is our known standard deviation. So we just take our variance, we take the square root. And here, this is our number of samples. Okay. Right. So this is this is where the number of observation or measurements comes into play. So the more measurements that you have, the tighter your interval is going to be. Okay. And then this value of C, okay, this value of C, you can think of it as kind of like a scaling factor that's based on the random number or the random distribution that we're basing our assumption around. Okay. Right. So that's going to be kind of a constant kind of motif, I guess you can say, for both confidence intervals and hypothesis testing, where basically every calculation that we do, you're going to need to look up some kind of scaling factor or some kind of coefficient in a table. Okay. So that C there, we kind of discussed the table values for last time, but basically you're going to look up that value in a table. Okay. All right. And then the value for C, when you look up the table, that's going to depend on your confidence interval. Okay. So that's just a very, very quick overview of kind of what we talked about last Thursday. I know, the thing with probability and stats, I think the calculations themselves are not, at least in my opinion, they're not too complicated, right? So we're not doing, integrals or complex derivatives here or anything like that. It's a lot of times just a very simple arithmetic. But I think the part that I think gets kind of confusing and intimidating is just there's just a lot of terminology. There's a lot of new variables that are there, and so I think it pays a lot to kind of go through these terms and these concepts just because they are quite different from I think most. Okay, so today we're going to continue this discussion, and so we're going to go over what would happen if we do not know the variance beforehand. Okay, and so we're going to look at situations where this variance is unknown. Okay. It's gonna present a slight twist, a slight difference in our kind of our methodology here. It's going to change the scaling factor that we look up, but for the most part, it's very similar to the process that we went through for this. Okay, but that was just kind of a recap from last Thursday. Any questions on this so far? Okay, all right. So let's go ahead and take a look at cases where we do not know the variance. Okay. So practically speaking, when you are computing confidence intervals, so like when you're doing this for your lab testing, or let's say you're doing this out, after graduating, you're working in lab. Most of the time, you're going to be working under this type of scenario, right? Most of the time, when we say that we don't know the variance, kind of what we're kind of implicitly saying is that there are multiple factors of uncertainty that could affect our measurements. Okay. So the example that we did last Thursday is honestly very kind of contrived, right? It was it used kind of a very poor ruler on purpose. But most of the time, when for the situations where you are interested in the uncertainty, they're going to be in situations where there's just multiple factors kind of affecting the uncertainty at the same time. Okay. And the thing with uncertainty is that when you have multiple factors, contributing to uncertainty, the way that they actually interact with each other and kind of manifest is actually quite complex. And there's actually very complicated math that kind of goes into that. But just for the sake of for our class here, so when there's multiple factors of uncertainty, we just say that variance is going to be unknown. Okay. Okay. And so in these cases, we can't pre-assign our variance beforehand like we did in the last example. So the variance is something we're going to need to measure based on our observations. Okay. Or I should say computed. Okay. Right. And so when we compute and remember, whenever we compute the variance based on observations, we're no longer working with the true variance or the true standard deviation. We call this the sample variance. We call that sample variance S squared. Okay, so it's no longer sigma squared, but S squared. Okay, and so what you're going to see is that when we go through the procedure of computing confidence intervals, we're going to essentially replace the sigma that we had in our formula for k up here with S, but that is going to change how we compute the scaling factor C. Okay. Okay. All right. So let's go through the procedure. We'll go through the procedure and then we'll do an example and then we'll kind of wrap up confidence intervals. Okay. Okay. Step one. So just like for the case when we have our known variance, step one is going to be to select a confidence level. Okay. So confidence level is something that you pick, and so that's the amount of confidence that you want to have in your computations or your measurements here. Okay. So for this class, just to make sure that everyone gets the same answers for the problems, this is something that I'll give to you, right? And so for this class is not something you have to worry about. But in reality, this is something that you have to kind of choose based on your application. Okay. So there will be some applications where maybe you want to be absolutely precise, like you're working with an application where just the margin of error is very small. And so when you do your computations here, you set your confidence interval to be very high, right? Or maybe you're working in a situation or application where, you can afford some uncertainty. You can afford some, measurements that are outside your interval. So you can pick a lower confidence interval and that kind of lowers the requirements on your testing. Okay. But what you select for that is kind of application specific. Okay. Number two. So step two here, we need to compute a quantity. So this is where things start to deviate a little bit from the previous procedure. Okay, so we're going to compute a quantity called f of c, and this is going to be equal to 1/2 1 plus gamma. Okay, where gamma, we're just going to plug in the confidence interval that you define up. Okay. So what is this f of c? So you can see that this variable here, it contains c, or at least it's a function of c, right? So this is eventually what we want, right? Because this c is what we're going to plug in to compute our k, which is our interval quantity, okay? But the way that we actually compute that will be a bit different compared to what we did before, okay? Because now, right, since we're working with an unknown variance beforehand, we actually have to use a different random distribution in order to model our uncertainty, okay? Okay. And so since the variance is unknown, right? Previously, we used a Gaussian distribution to model the uncertainty in our random variable. But since our variance is unknown, we are going to switch over to what's called the t distribution. Okay. All right. So the t distribution, it actually looks very similar to the Gaussian distribution. It's kind of a symmetric distribution with the singular mean, but the way that it decays is slightly different than the Gaussian, right? Okay. So what does that mean for us? And so that means that when we look up the value for c, we need to look it up in a different table. And so if you have the textbook, this is table A9 in the textbook in the appendix. Okay. But you don't need the textbook. This is one that I've kind of copied and put it online. So this is in a handout that's on Canvas. Okay. All right, and so I'll give you kind of a preview of that table. I'm not going to write the whole table here just because it's just a lot of values, but I'll show you kind of what it looks like. Okay, so the table looks like the following. And so the first column here for the table is a column for f of c, right? And so you're going to see various values down this column right here. So we're going to have, it starts at 0 0.5, 0 0.6, 0 0.7, 0 0.8, 0 0.9. Okay. And it continues. There's more to it. Okay. But that's as much as I'm willing to write right now. So what we computed here earlier, this f of c, we're essentially going to look into the table for that particular row. Okay. So let's say we compute our f of c. Our f of c is, let's say 0 0.9. We're going to look in the row for 0 0.9. Okay. And then every column after this will refer to certain degrees, what we call degrees of freedom. Okay. Which is a little odd of a name for what this is, especially given the context of what we're using it for. But that's the name that they've decided for. Okay, so what you're going to see is that we're going to have different columns here that refer to different numbers of degrees of freedom. So first column will be 1 degree freedom, 2, 3, 4, 5, 6, 7, 8. Okay. And it continues. It's a very large table. So you can see the degrees of freedom is actually, it goes up to even, I think, 50 or 100. Okay. Okay. And then in the table itself, these are going to be your values for C, right? So for instance, for the first row of this table is actually all zeros. Okay? So you can't have an f of c value of 0.5, which makes sense because an f of c of 0.5 means a confidence of 0. So you got to have more confidence than 0%. Okay. Next row is 0.32, 0.29, 0.28, 0.27, 0.27, so on and so on. Okay. All right, and then there's a lot more values in the table itself. Okay. All right, so the way to use this table is that depending on your value for f of c and depending on the number of degrees of freedom, you're going to look at that entry in the particular table. Okay. All right, so let's say that, let's say for instance, we have a f of c value of 0.6. Okay. And let's say we have a degree of freedom of 4. Okay. That means our value for c is going to be wherever those two intersect. Okay, so this is going to be c that we just computed. Okay. All right. So then that begs the question of what is the degrees of freedom? So the degrees of freedom is simply refers to the number of observations that you have minus 1. So degrees of freedom is equal to n minus 1. Where n, of course, is the number of tests or the number of measurements or number of observations. Okay. So compared to our previous case with where our variance was known, the main deviation between the two methods is really kind of step 2, right? So just make sure that you use the correct table and make sure that you compute the degrees of freedom and f of c, all of that kind of correct. Okay. Okay, any questions on this so far? Okay. All right, so that's step 2, right? So step 2 is kind of the longest one here. Okay. Step 3, once you have your value for C, you're going to compute your sample mean and sample variance. Okay. And so these are going to be based on your observations. So remember, sample mean x bar is equal to 1 divided by n, summation I is equal to 1 to n of xi, right? So you're just going to sum up all of your observation, divide by the number of observation. That's your mean, right? And then your sample variance, remember, is 1 divided by n minus 1, summation I is equal to 1 to n of xi minus x bar quantity squared. Okay. So the sample variance might be a little bit tedious to kind of compute, but it's not difficult math. It's just kind of annoying and kind of tedious to do. Okay. Okay. All right, and so of course that's going to depend on your observations. We'll do an example with that after this. Okay. All right, so once you have those, we can go move on to step 4. Step 4 is to compute your interval. Okay. So we have our variable k here. So k is equal to c times s divided by square root of n. Okay. So everything we've computed up until that point, just make sure that whatever you get for the sample variance, you take the square root before you plug in for n, okay? Or plug in for k, excuse me. And then we have our interval. So our interval here is x bar minus k is less than or equal to x, less than or equal to x bar plus k. Okay? And that right there is the interval that we report. Second? X bar, yes. Oh, the one in the middle. Oh, yes. Thank you. Okay, so a lot of terms, a lot of procedure here, but you'll see that when we actually do an example, it's actually quite straightforward. Quite easy. Okay. All right, any questions on this before we jump into that example? Okay, all right, so let's do an example. Okay, so let's say in this example, we are working on an application where we want to find the flash point of diesel oil. So if you're unfamiliar, flash point is basically the temperature at which when you heat up an oil, it kind of flashes. So it kind of splash and so it's a dangerous you typically don't want to get your oil this hot. Otherwise, bad things can happen. People get hurt. Okay. Okay. So so this experiment, this measurement is somewhat dangerous, and so the amount of measurements that we have are limited, right? So this is not something we can just measure endlessly. And so the measurements we have 5 measurements here, okay? Right, and so for the first test, we obtained a flash point of 144 degrees Fahrenheit. Second test, we got a flash point of 147 degrees Fahrenheit. Third test, we got 146. Fourth test, we got 142. And then last test, we got 144 degrees Fahrenheit. Okay. And so for this problem, we want to determine, just because this is a very sensitive kind of application here, we don't, typically we don't want to be wrong for our whatever statement that we make based on these tests. And so we're going to choose a fairly high confidence level. So based on these measurements, let's determine the 99% confidence interval for the average flash point. Okay. So we're basically going to apply our methodology that we just kind of went over, our 4-step process to this problem. Okay, so let's just go right through the 4 steps. So step 1, define confidence level. Right, so luckily it already is defined for us. We just have to put it in decimal form. Okay. So for a 99% confidence interval, that means our gamma is 0.99. Okay, good. Step 2. Right, so now that we have our confidence interval quantified here, we can compute f of c. Okay, so remember the formula for that is 1/2, 1 plus gamma. Okay. So we're just going to plug in our value for gamma there of 0.99. We add 1, we take a half, we get 0.995. Okay. Now let's compute the degrees of freedom. Okay. So in this case, the number of measurements that we have is 5, right? So we compute degrees of freedom as n minus 1, where n for this problem is 5. Okay. That means our degrees of freedom here are going to be 4. Okay. So based on these 2 pieces of information, we can look this up in table A9, or the table for the t distribution. And we get a C value of 4.60. Okay. All right, so that's easy. Okay. Next step, now that we have our value for C, we can compute our sample mean and our sample variance. So for the sample mean, we're just going to take the average of all of our measurements there. Okay, so we're going to take 1 divided by 5 times the sum, 144 plus 147 plus 146 plus 142 plus 144. Okay. All right, so we can punch that into our calculator. We get a mean of 144.6 degrees Fahrenheit. Okay. All right, so then now that we have the sample mean, we can compute the sample variance. Okay, so variance here S squared is equal to 1 divided by n minus 1, so 1 divided by 5 minus 1 times summation of each of our measurements subtracted from the mean squared, all added together. Okay. All right, so we have our first measurement here is 144. And so we're going to subtract the mean, so minus 144.6 quantity squared plus 147 minus 144.6 quantity squared plus 146 minus 144.6 quantity squared plus 142 minus 144.6 quantity squared plus 144 minus 144.6 quantity squared. Okay. All right. So the subtract, I know it's a lot of terms here, but just remember for every subtraction here, we're taking basically each individual measurement and we're subtracting the sample mean. So everything I've underlined there is just simply X bar. Okay. Bless you. All right. So we punch that into our calculator here. We get a sample variance of 3.8. Okay, so our measurements are actually pretty tight in this case. Okay, so a variance of 3.8 when our mean is 144 is actually very, very good. It's our measurements are pretty precise in this case.
Can you explain that one a little bit more?
The variance?
The 3.8. Why it's so good.
Oh, yeah. So the variance basically describes how varied our different measurements are. And so for this case, we actually don't have a lot of spread. And so you can see everything is pretty clumped together. So we have 144, 147, 146, 142, 144. So compared to the mean, so the mean we got for this is about 144 also. So a variance of 3.8 is less than it's 2 orders of magnitude less. Exactly. So there's not that much spread. So it's better than let's say we got measurements of like 160, 130. So that would be a lot more spread. All right, and then when you compute the standard deviation, it's even better. Remember, standard deviation is simply just the square root of the variance. So we take the square root of the variance that we just computed, and we get 1.9. And that is equal to S. Okay. All right, so we have everything that we need. So last step here, step 4, is to compute our interval. Okay. So we're going to have K. This is going to be equal to S, which is our sample standard deviation, multiplied by C, which is what we computed in step 2, or I guess we looked it up in a table. We divided by square root of N. Okay. Now, even though we don't have that much spread in the data, we don't have that many measurements. And so our interval here is actually going to be somewhat large. Okay. So our interval in this case is 4.01. Okay. That means our interval For the our estimated value for the flash point is our mean 144.6 minus or plus 4.01. That's on the upper end. And on the lower end, we have our mean 144.6 minus our sample standard deviation 4.0. Okay. So we just simplify this very quickly and we get 148.7 and 140.5. Okay. All right. And so remember, this interval here, we computed with a 99% confidence. And so if we were to take another measurement, so let's say that, let's say we either did another experiment, or maybe, we actually put this diesel oil into practice, right? There is only a 1% chance that our flash point will be outside of this interval. Okay. Right. So these problems don't seem like they're very exciting, at least mathematically. There's not that many computations to do. But a statement like this you can see is very powerful, right? Because a lot of times, when you're working in engineering applications, a lot of times you're going to be making decisions based on what you compute, right? And so for this case, right? So let's say you're designing an engine that's going to make use of this diesel oil, right? If you know that there's a 99% chance that your flash point is going to be between these values here, that's something you can design around, right? And you can design around a 1% probability. Of course you're going to have fail safes. You're going to have things to account for that 1% chance. But for the most part, this is a quantified value of confidence that will help your design, right? Because it's one thing to say that yes, there's going to be variance in what we observe, but if you can't quantify that variance, that's not something you can really work with, right? At least not in a tangible way. And when you do engineering, you have to be able to make these kinds of decisions. You have to be able to make design choices, and it really helps to have any kind of uncertainty or probabilities all quantified as clearly as possible so that you kind of really know the risks. Okay. And our next section is going to go into that a little bit deeper. All right. Any questions? Any last questions on confidence intervals before we move on? Okay. All right. So for the last 30 minutes of class today, let's talk about the next unit here, which I call hypothesis testing. Okay. So I think when people hear the term hypothesis, I think you automatically start to think of like some kind of scientific study, right? So a hypothesis, the definition of a hypothesis is just a theory or a guess, right? I think in school, I think they call it just is an educated guess, but hypothesis is a statement about what you think will happen in a given situation. right? And that could be anything, right? It doesn't strictly have to be in a science and engineering, um, you know, circumstance or situation, although, we will be talking about it in that situation, right? Okay, so the thing with hypotheses is that, we don't just leave hypotheses as they are, right? Oftentimes we either want to prove a hypothesis or we want to disprove a hypothesis. And the way we do that is by conducting experiments and collecting measurements. Yes.
Would we be rejecting the theory, not the hypothesis?
In this case, we're going to use the hypothesis, and so the hypothesis you see, we're gonna use it in a way to like make a statement on a certain situation, and then based on what we observe, we're going to either say that that statement is false or that statement is true. Yeah, but technically yes. So we can use measurements to reject theories and accept theories as well. Yeah. All right. So I think, at least, for the most part, terminology aside, I think that's generally how hypotheses are kind of presented in a scientific perspective. Okay. Now for engineering, we're going to go a step further, right? And so you're going to be making hypotheses a lot about certain types of, situations, what's going to happen, the values of certain quantities, right? But the important thing that we have to kind of worry about is that based on a hypothesis or based on the result of a certain test, we have to make decisions. So we'll do kind of a very kind of simple, but I think hopefully illustrative example after this. Okay. Okay, so what we're going to go through in today's lecture and Thursday's lecture is kind of the formal theory or the formal procedure through which you can actually take a hypothesis and either accept it or reject it based on the measurements or the observations that you have. Okay. All right. Any questions on? So this is just kind of simple definitions, just a simple introduction. I think once we do an example, it'll be a bit quick. Okay. All right. So let's just jump right into an example, and I think you'll see that you'll see all the calculations just based on this example. Okay. So let's say that we are working in an application where we need to purchase some kind of structural wire. So that structural wire is going to be required to hold a certain kind of load, right? Maybe it's supporting a weight, or maybe it's supporting a certain force. Okay. Right. So let's say that we're looking on our supplier. So let's say we're on McMaster Car or something like that, and we find a wire that's at a reasonable price, and the supplier claims that the wire can hold up to 200 pounds of force. right? So what you can say is that the breaking limit of this wire is 200 pounds, right? So any weight or any force that is applied that's over 200 will cause the wire to fail, okay? So we look at this and we're like, perfect, that's exactly what we need for our application. Right? So we need 200 pounds of load. The supplier is saying their wire can hold 200 pounds. That's perfect. It's like a match made in heaven, right? It is a little bit close, and so we can say that, you know, maybe this is a little bit too perfect, a little bit too close for comfort. And so, you know, before we actually put it in practice, you know, we want to kind of test, or we kind of want to verify the supplier's claim that their wire can indeed hold 200 pounds. Okay. And so before we put this in practice, we order some samples from the supplier, and we're going to run some tests, right? And so we're basically going to apply force. We're just going to put it into a load machine, and we're just going to keep applying a tensile force until the wire snaps or the wire breaks. Okay. And so based on the results of this experiment, we're either going to make a decision whether we're actually going to go with the supplier and order this wire, or maybe we'll move on to something else, something that maybe fits our needs at the time. Okay. So we're going to use this example here, or we're going to use this kind of, you know, theoretical situation to kind of illustrate the procedure that you need to take to test a hypothesis like this. Okay. Okay. All right. So I think we'll go through that procedure. I think we'll have just enough time for that. We'll pass back the exams and then we'll call it for today. Okay. All right. But any questions on this so far? Okay. All right. So first step in this process is we need to form a hypothesis. Okay. All right. So usually your hypothesis, at least for situations like this where we have a quantifiable hypothesis, usually our hypothesis is going to be that whatever the theoretical value of whatever we're testing is going to be equal to a certain whatever we want. So usually our hypothesis is some kind of equality statement. Okay. Okay. And so for our case, you know, it's already kind of written out for us. And so our hypothesis here is going to test the supplier's claim that the wire could actually hold 200 pounds of force. Okay. So if we define this mu here will be the breaking limit. Okay. Right. The breaking limit for our wire, we're going to say that this is equal to 200 pounds. Okay. Okay. So the hypothesis for the most part is usually pretty simple. Okay. Okay. Step 2. So I think this is where it gets a little bit interesting. So step two, we're going to form something that we call an alternative hypothesis. Okay. So again, it's another term, probability and stats, they love having terms, right? So what is an alternative hypothesis? I think it's a little bit confusing because I think a lot of times when you read about alternative, they'll say it's just a counterpart to the hypothesis, which is not helpful at all. And so this is kind of my definition for alternative. So the alternative hypothesis basically defines the criteria under which we will reject our original hypothesis. It can be a little bit tricky to define the alternative because you're gonna see that on Thursday there's multiple ways or different ways that we can define the alternative, and how we define the alternative is going to be different depending on the application. Okay. And so you have to have a little bit of ingenuity. You have to kind of read a little bit into the context to define a proper alternative. Okay. So for this particular application, right, we're looking at a wire, right? And we're looking at the wire for a specific application that requires 200 pounds of load to be supported. Okay. Now, let's say that, maybe and I think generally when you're purchasing something, you assume that, I think just the cynical person within me will say like, oh, it's not going to be as nice as what the supplier claims, right? And so you buy a phone that says, oh, it has 13 hours of battery life. I think just the cynical person is like, oh yeah, it probably only has like 5 hours of battery, right? But there could be a possibility that maybe the supplier is underselling their product, right? And so in the situation where, let's say that we run our tests and the braking limit is actually over 200 pounds, right? That's the situation where we're not going to be mad at that, right? So we're going to say we're getting more braking limit than our money's worth, right? And so in the case where we get a higher braking limit, we can still accept our original hypothesis, right? That doesn't change our decision making, right? The only bad thing is that, let's say we run our tests and the braking limit is actually less than what's advertised, okay? So that is our alternative in this case. So our alternative, sorry, I need to drink some water. The alternative in this case is, the actual braking limit is actually less than 200 pounds. Okay. So if we find during our test that the braking limit is less than 200 pounds, and it's less than that by a significant margin, okay, so we'll define significance in a second, then that would be a situation where we reject our original hypothesis and we look at a different supply, okay? Right, and so implicitly what we're saying is that if our braking limit is actually greater than 200 pounds, right, then we still accept our hypothesis because that's an outcome that we're still happy with. Okay. So you want to be careful with how you define your alternative, and it does change kind of how we do the rest of the steps later on. Okay. Step 3. Okay, step 3 is we need to define what's called a significance level. And so the symbol for significance level is alpha. Okay. So this is where uncertainty comes into play, right? So, whenever you run an experiment, we always have to kind of make the admission, we have to kind of, concede that we cannot run an infinite number of tests, right? There's a finite amount of tests that we have. And so there's always a probability, right? We hope that it's a very small probability that the results of our tests are not a true representation of whatever the true quantity is. Okay, so this represents the low probability that whatever we find from our measurements, is not an accurate representation, or whatever we get is we're going to get a different result than what we got from the tests. Okay. All right, and you always have to have some significance, right? It's usually going to be low, right? It's usually never going to be very high, but you can never set a significance level to be 0%, because in order to have true certainty, you have to, realistically, you have to run, millions and millions of tests, which is not feasible. Okay. Okay, so usually for most cases, we're going to set a significance level of that's going to be fairly low. Okay, so for this example here, we're going to go with a fairly modest significance level. So we're going to set our significance level to be 0.05. So this represents a 5% probability that our tests were poor. So, if you've read any kind of technical report before that kind of deal with large data sets, you might have heard the term statistically significant. That kind of has to do with this kind of concept here. Okay. So when people say something is statistically significant, what they're saying is that the probability that, whatever outcome that they observe, right, the probability of that being false should be very, very low. Right. So their significance level in that case would be something like, maybe less than 1% or something like that. Right. Now, the way that they compute significance level in those situations are a bit more complicated than what we're going to do. We're doing a fairly simple calculation, but the concept and the understanding is kind of still the same. Okay. Because even with the large data set, there is still a probability that, let's say that you poll, let's say everyone on campus here, what their favorite pizza is, right? And so you could get a dominant answer, right? But, there's still a probability that, maybe everyone here at Cal State Fullerton has poor taste and, is not really representative of the general population, right? So there's always going to be some significance. And so you always have to kind of admit that. Okay. All right, step 4. Step 4 is to use a random variable distribution, which for our case is just going to be the t distribution. So that's the same t distribution that we talked about, at the end of our confidence intervals. Okay. right? So we're going to use the t distribution to determine our scaling constant. Okay? So we're going to use the exact same table, and we're going to use it in almost the exact same way to compute our value for that constant c. Okay. And so remember, to use that table, you need a couple pieces of information. Right, and so one thing you need is f of c. So the value for f of c is going to take a different value here. Okay. So it's going to be either equal to our significance level by itself or 1 minus significance level. Okay. We'll talk about kind of, probably on Thursday, we'll talk about, which case that you use. Okay. Because there are different situations where you're going to use one or the other. Okay. Right. And then, of course, you also need your degrees of freedom. Okay. Where your degrees of freedom is going to have the same definition as before. It's going to be n minus 1. Okay. Okay. All right, step 5 is we're going to compute. So this is when you actually run your tests, right? So you take your measurements. Okay. And then after you compute your measurements, you can compute the sample mean and sample variance. Okay. Okay. And so just because I want to end 5 minutes early for these, pass up the exams, I'm going to give you the formula for step 6. So step 6 is going to be the most defining characteristic. So I'll give you the formula for this first, and then we'll kind of jump right into this on Thursday. Okay. So step 6 is to either accept or reject your hypothesis. Okay. Based on the following formula. Okay. Okay. So we're going to compute t is equal to x bar, our sample mean, minus mu, where mu here, that's our hypothesized value, divided by s, which is our sample standard deviation, divided by square root of n. Okay. Okay. And then what you're going to do is that once you compute t, you're going to compare this to the value of c that you computed in step 4.
That's divided by square root n.
Square root of n, yes. Right, and then depending on the relative value for t compared to what you got from c from step 4, you're either going to accept or reject your hypothesis. Okay. Okay, but we'll get into kind of the details for that next time. So I did want to leave the end of it early to pass that exam. Any final questions on this before we wrap it up for today?
Wouldn't that best case scenario t will be 0?
So if t is 0, that means your observed mean or whatever you observe is right on the nose of your hypothesized quantity. And so in that case, you're going to accept the hypothesis.
But so I would expect it to be like less than 1, I guess.
It depends. And so it depends on if what you measure is higher than your hypothesis value or lower than that. If it's higher than that, it's going to be a positive number. If it's less than that, it's going to be a negative number. Yeah. But you'll see, I think, and the value for C will be positive or negative depending on what alternative we pick as well. Yeah. All right, cool. All right, so thank you guys. So I have your exams up here, so please come get them. I will split them into version A and version B. Or maybe not. I think I mixed it up a little bit. So I apologize. Yeah. All right. So if you're on Zoom, I'll bring the exams again on Thursday for you guys to pick them up as well. So thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you on Thursday. Yep.